Hello. In this video, I'm going to work through example 1.9 from the text. Before watching this video, you should have already read through the first part of this section, if not all of it. So you should understand what a statement is and what an open sentence is, along with other terms like domain and truth value. So with that being said, if you haven't done that yet, pause the video here and read through that first part of the section and understand what we're talking about. So in this example, we're asked to consider the following open sentences where n is a positive integer. So that is the domain for each one of these open sentences is positive integers. That's what n is. In a way, we're kind of thinking of these open sentences like functions, right? Only when I put a value into an open sentence, what I get out is not a number like a function you might have seen. Instead, what I get out is a statement. So for every positive integer n I plug in here, say p1 of 0, I get a statement. So for instance, p1 of 0 would be the statement absolute value of 0 plus 1 is equal to 0. Well, 0 plus 1 is 1. Absolute value of 1 is 1. And so this is equivalent to the statement 1 is equal to 0, which is false. So in this case, P1 of 0 would be false. So that just to illustrate the point that open sentences, right, plug something in, I get a statement out that's either true or false. An open sentence on its own, just as is like this, doesn't have a truth value to it. I need to plug something in. So what we're asked to do in this example is to find all positive integers n such that each open sentence is true for those positive integers n. So find all positive integers n that make the open sentence true. So for these, we have to do a little bit of thinking, but none of these are too difficult if you use some background knowledge. For instance, here I have absolute value of n plus 1 is equal to 0. Well, if I'm taking the absolute value of something, the result's always going to be greater than or equal to 0. So the only time an absolute value is equal to 0 is if the inside itself is 0. So what that tells me is that in order for P1 of n to be true, n has to be, or n plus 1 rather, has to be 0, and therefore n is equal to -1. So P1 of -1 would be the statement -1 plus 1 equal to 0. That's equivalent to 0 equals 0. That would be true. The only issue here, though, is that -1 is outside of our domain. This example is asking for all positive integers n that satisfy this. So we have to toss this one out. It's not looking for negative numbers. And by that logic we just went through, -1 is the only thing that makes this equal to 0. And so there are no positive integers n for which this is true. So we'll say there are no positive integers n such that P of n is true. So we've solved it. There are none. Maybe I should write these solutions in blue. Moving on to P2 of n, if n squared minus 4 is less than or equal to 0. So again, we'd like to find all positive integers n that make this true. If we want, we could rewrite this a little bit. I'll do this a little bit differently than the book runs through. I'm going to focus on this n squared minus 4. If you were to say plot this in a calculator, something like that, and actually graph the function n squared minus 4, you would see, and just by some analysis, you'd see it has two roots, -2 and 2. It's parabolic and opens upward, and so it looks something like this. What this means is, since we're looking for when this is less than or equal to 0, that means things inside of here, they'd have to be inside of this gap between -2 and 2. So if we're looking for all real numbers that made this true, it would be this interval of real numbers. But we're not. We're looking for positive integers n that make this true. So all the integers in here, right, we would have -2, -1, 0, 1, 2. But we just want the positive integers. So -2, no, -1, no, 0, no. 1 and 2 would be our only options. So we can say P2 of n is true when n equals 1 and n equals 2, and those are the only two. So I could add something and say, and false otherwise. All right, moving along, P3 of n squared minus n minus 6 is equal to 0. I'm going to when this thing is equal to 0. So this is like finding the roots of a polynomial, right? N squared minus n minus 6. I want to know when that's equal to 0. You might remember back to, I don't know, a calculus class, if you've taken this, or a pre-calc, something like this, algebra, where we can factor n squared minus n minus 6. So in this case, right, I want two things that multiply to -6, but add to -1. So let's see, -3 plus 2. So n squared minus n minus 6 is the same thing as n minus 3 times n plus 2, giving us the solutions. So if this is equal to 0, then n equals 3, or n equals -2. So -2 is not a positive integer, so we're going to throw that out. N equals 3 appears to be the only solution. So I could say here, maybe I'll write it a little bit differently than the last one, P3 of 3 is true, and P3 of n is false for all n not equal to 3. Positive integers n not equal to 3. Sorry, I'm not being consistent with my colors. I'll try a little harder. This last one's maybe a little bit challenging. N plus 1 over n less than or equal to 2. So one thing to note here, right, we could list the positive integers that this could possibly be, right, like 1, 2, 3, 4, the counting numbers, and up. Notice that n is an increasing function as well as 1. 1 over n is not an increasing function, but n is. And so as soon as I get to 2, as soon as I have n equal 2 here, I'd have 2 plus 1/2, which is 2.5, which is not less than or equal to 2. And it's not too hard to see that if I plug anything else bigger than 2 into this, I'll necessarily be greater than 2. So pretty quickly we can see that the only solution to this, or the only thing we should check, is when n is 1. So we can identify, this should be P4 of n is this statement. So we can check P4 of 1. That would be the statement 1 plus 1 over 1 is less than or equal to 2. That's equivalent to 2 less than or equal to 2, and that is a true statement. And right, by that logic I mentioned before, we can say P4 of n is false for n greater than or equal to 2, for positive integers n greater than or equal to 2. So that's example 1.9. We get to play around a little bit with open sentences, remind ourselves what those are, and then actually solve some problems and figure out when an open sentence is true. All right, that's it for this one.